Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on the overview of waste treatment plant Hanford site will be given by Dr. David Peeler. Doing the introduction today is Dr. Patricia Pavier. She's the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory, and she's also the chair of the Gen 4 International Forum Webinar and Training Working Group. Patricia?
Thank you very much, Bertha, and good morning, everyone, or good evening, depends wherever you're listening from. It's a pleasure today to have with us Dr. David Peeler. He received his PhD in ceramic engineering from Clemson University, and over the past 25 years, he has focused on glass formulation development, developing alternative processing strategies to improve operational flexibility and waste throughput for the Defense Waste Processing Facility in Aiken, South Carolina, and for the waste treatment plants in Hanford, Washington State. He currently serves as the Environmental Management Deputy Sector Manager at Pacific Northwest National Laboratory, in which over $45 million of R&D is annually performed, focused on waste processing and environmental remediation. Dr. Peeler serves on the External Advisory Board for Clemson University's Material Science and Engineering Department, and he is an adjunct professor at Clemson. He's also a fellow of the American Ceramic Society, has over 85 external peer-reviewed publications, and over 300 internal technical reports. He has issued 3 patent disclosures with 1 international patent awarded. So it's a great pleasure to have you, David. I just cannot wait to listen to your presentation. And without delay, I give you the floor. Thank you again for volunteering to give this webinar.
Patricia and Berta, thank you. Thank you for the introduction, and thank you for the opportunity. And for those on the call, welcome. I appreciate you taking time out of your day to attend today's meeting. As Patricia mentioned, I will be focusing on the waste treatment plant at Hanford, but for some perspective or to establish a framework. Excuse me. This really is not going to be a WTP update from a design construction phase looking into transitioning into operations. But we're going to focus on the key elements of the Hanford WTP flow sheet and how those different unit operations are actually integrated. And once we define those major unit operations, I'll take a deeper dive into the immobilization unit operation or the vitrification process and discuss how the vitrification facility is technically underpinned to ensure safe and efficient operations. Before talking about the challenge that you're seeing on the screen right now, I recognize we have likely have a broad spectrum of participant knowledge and backgrounds. So my hope today with this presentation, that those of you who are familiar with that are not familiar with the vitrification process, leave with a high-level perspective and a general understanding of the complexity of the process, or perhaps you may find some similarities and integration issues that I'll talk about in the systems that you're working with. For those of you that are more familiar with the vitrification process, I hope this overview provides or potentially confirms some of the lessons learned or things that you may have experienced as you're dealing with your similar processes. So as Patricia mentioned, without further ado, what is the challenge? We have approximately in the US about 90 million gallons of radioactive liquid waste currently stored across the DOE complex. That waste is currently stored in 1 million gallon tanks. That's the approximate size. They vary in size a little bit. To kind of give you some perspective of those tanks, this is an 8-pack, if you will, of tanks during the construction phase. This would be an aerial view looking down on those tanks of today, where you have only access to the tanks through the ports in the top. That 90 million gallons that are spread across the sites or the DOE complex, it's primarily stored as a liquid waste. There are 3 main components of the tank waste. The first component being the sludge. You consider that to be the solids that usually settle to the bottom of the tank. We have a salt supernatant, which is a liquid fraction, if you will, that sits on top of the sludge fraction in an undisturbed or unsettled tank. And then you have a saltcake fraction, which is essentially dried or dried supernatant. We'll be primarily looking at the flow sheet that's going to process the supernatant for WTP today, but I'll use some examples on the sludge side, which is the high level waste side. Obviously, the 90 million gallons of liquid waste stored across the DOE complex represents a significant environmental risk, and therefore there's a lot of fundamental applied research that's being done, not only to develop and mature the technologies or these innovative solutions, but to deploy those innovative solutions to meet the mission. That mission really is pretty simple, if you will, in concept. It is to retrieve the waste from the tanks, to perform any kind of pretreatment of those waste, to prepare them for an immobilization process, to put that into a waste form, and then ultimately to dispose of those waste forms in a repository of some sort. Again, what you may hear me refer to a tank farm throughout the talk. And when I talk about a tank farm, I'm talking about a complex of tanks that are holding that waste or containing that waste. And one thing you should know that the waste in these tanks not only vary from top to bottom, if you will, but between tanks as well as between tank farms. So it is a very complex concoction of elements that we'll talk about later, which is a significant problem in terms of meeting this mission need. But ultimately, the mission is to retrieve these waste, immobilize these in a stable waste form for long-term disposal. So kind of an outline of the overview of the presentation. We'll talk about the integrated flow sheet. I'll mention the flow sheet aspects in a second. We'll talk a little bit about the waste generation and the troubles components. I'll be talking about this through the lens of the vitrification facility, not so much about the processes that generate the waste. We'll take, again, a deep dive into the mobilization and operations, since I spent the majority of my career in this space. Specifically, we'll talk about the batch to glass conversion process. We'll talk about some critical properties, process and product performance properties of the glass that need to be met, and why they're needed and how they relate to operations. We'll ultimately talk about models and algorithms that ultimately control the process, and then we'll talk about operational windows and operational flexibilities. And this will be my key message today, is terms of operational windows and operational flexibility, and hopefully you walk away with that. I'll sprinkle in a couple of operational considerations or examples and show you why it's important not only to focus on your particular unit operation, such as the vitrification process, but seeing that entire landscape, seeing the entire landscape of the whole flow sheet, if you will. Then I'll wind up talking about a ORP program, the EWG program, Enhanced Waste Blast program, and the impacts it's having on the particular mission. So before I show you the Hanford integrated flow sheet, I wanted to kind of define what I mean by flow sheet. Or you can think of, when I refer to a flow sheet, I know there's a lot of different contexts out there. You can think of this as material flow, or the series of complex reactions or chemical processes that occur to meet that mission. That mission, again, is to retrieve, pretreat, immobilize, and dispose. So when you hear me say integrated flow sheet, that's the process that I'm talking about. Well, the one at Hanford is probably the most technically challenging efforts in the DOE complex, if not internationally. And the baseline flow sheet for Hanford originally looked like this. We have waste stored in the tanks. We'll talk about in a minute. There's 177 tanks, about 55 million gallons at Hanford. That waste was going to be retrieved. Both the sludge and the salt or supernatant fractions were going to come into a pretreatment facility. The pretreatment facility was going to split that waste stream into two different vectors, if you will, a low activity waste and a high activity waste stream. The low activity waste stream would come into the VIP facility, into a receipt vessel, where depending upon the composition of that feed vector, we would add glass forming chemicals to that waste stream, make a melter feed targeting a specific glass composition that we would like to produce, that glass composition or that melter feed would come into a high temperature melter. This operates at 1150 degrees C. It would be converted into a glass product, and that glass product would be poured into a can, and those cans would be ultimately disposed of, and for the LAW side, on site in a near surface land disposal. On the HLW side, we do the same thing depending upon the incoming feed vector, the composition of that incoming feed vector. We would add glass forming chemicals to make a melter feed targeting a specific glass composition. That composition would, that melter feed would come to the melter again at 1150, produce canisters that ultimately go into a cheap repository, cheap geological repository. Due to some pretreatment technical issues, the Department of Energy decided to take a slightly different route to start operations sooner. You will hear me refer to as the direct feed low activity waste, or DF-LAW flow sheet. In this particular flow sheet, they are focused on the LAW side, or the low activity waste side, obviously by definition, which is primarily the supernatant or the dissolved salt cake. That salt cake and supernatant would be retrieved. It will be coming to a pretreatment facility called tank side cesium removal, or TSCR, where they would do filtration ion exchange to remove the cesium, to keep the downstream unit operations contact handleable primarily. That decontaminated salt solution would come into the FIT facility into a receipt tank. Again, depending upon that incoming feed vector, you would add glass forming chemicals to target a specific glass composition. That melter feed would be pushed into a melter. That melter feed is converted into a glass, ultimately put into a canister, and then ultimately goes to a repository or the IDF disposal facility. So again, we're going to look at the integrated flow sheet, and that was an example, a really high level 60,000 foot example of the WTP integrated flow sheet. So I've talked a little bit about the tank farms. That is the tank farm strategies. We're not going to talk about a lot, but you can have retrieval and blending strategies and washing strategies that all can come into play on how the downstream feed vectors interface with either the pretreatment facility and ultimately the vitrification facility. And hopefully that'll become obvious in a few slides from now, how that tank farms can have a significant impact on downstream unit operations. In pretreatment, you could do unit operations such as aluminum or chrome dissolution. We talked a little bit about ion exchange or filtration, but again, you're trying to prep the feed, if you will, to come into the vitrification facility so those glass forming chemicals can be added to produce a glass product in that vitrification facility. In vitrification space, I'll define these terms a little bit later, but you'll often hear people talk about waste loading, melting rate, waste throughput, and a little bit on operational flexibility. Again, we'll talk about those in more detail in a couple of slides from now. But the one key message I want you to take away from today's lecture is this last bullet. Integration between these different unit operations is the key. Each one of those unit operations can be maximized, but that may not allow you to process or maximize the total efficiency of the entire flow sheet. So again, we'll talk about the systems approach and being able to look at the entire landscape of all these different unit operations and trying to make decisions in each unit operation space for the good of the entire flow sheet. I'd like to talk a little bit now about the composition of the waste, how these wastes were generated, and some of the problematic components. Again, I'm looking through the lens of the vitrification flow sheet when I'm looking upstream at the tank farms, and I want you to understand how these wastes were generated to kind of give you a little bit of idea about the complexity of the waste that are coming into the flow sheet. There are a lot of things that happen, as we talked about in the tank farms and the pretreatment facility, that really have to be looked at in terms of, can you mitigate some of these problematic components by retrieval strategies or blending strategies? What impact do these problematic components have on any kind of pretreatment decisions? You also have the transfer of the physical property issues, such as trying to transfer these materials between facilities within process vessels in terms of rheology, gel, precipitation issues, all those issues that we're not going to talk about, but they all they all play a part in the decisions that are made in each one of these unit operations to maximize this overall efficiency of the flow sheet. So I'm going to come back to this slide because there's a key point that I didn't talk about on that the challenge slide. We've talked about the 90 million gallons of radioactive waste stored across the DOE complex from the defense program. Again, it's primarily stored as a liquid waste, and those being the high level fraction of sludge primarily, and then you have saltcake and supernatant that are usually the low activity fraction, with the exception of cesium that's moved by ion exchange. That 90 million gallons in the DOE complex is spread across approximately 230 tanks at 3 primary sites. Those sites being Hanford in Richland, Washington, Savannah River site in Aiken, South Carolina, as well as Idaho. I will mention that Idaho has both a small volume of sodium granular waste, which is liquid, but they also have calcined waste, which is aluminum zerk calcine. We're not going to talk a lot about Idaho today. We're primarily focused on Hanford, and we'll make a couple of comparisons with Savannah River, but I wanted to point the Idaho calcine out specifically. We talked about the legacy waste being a significant environmental risk, and we talked a little bit about this fundamental and applied research that a lot of people around the complex are doing, not only to develop these innovative solutions and mature them in terms of deployment, to underpin or technically underpin the retrieval, pretreatment, and immobilization processes. But one thing that's really important, in particular from the perspective of this presentation, is I always tell the staff that I talk to, when you're doing that applied and fundamental research, I want you to have an eye toward implementation. Do your research with a focus. Do your research to define a baseline. That research may ultimately technically underpin the baseline flow sheet, but your research, once that baseline flow sheet is defined, your research should shift, if you will, to look for opportunities to reduce risk, reduce uncertainties, look for opportunities for improvement in this overall flow sheet. Now, this will come into play, this risk reduction and uncertainty and opportunity for improvement are going to come into play about the next to last slide, but I wanted to mention that specifically and just kind of keep that in mind. This slide shows kind of the volume and the curie spread across the DOE complex. I put West Valley on here. West Valley has already converted their waste and has a couple hundred canisters sitting in high-level waste space ready for disposal. I have Idaho sitting here, but I want to focus on Richland and Savannah River. The blue bars talk about the volume of waste. The red bars give you kind of a comparison to curies. And obviously, you look at the volume aspects, and at Richland, we have more volume, but less curies. And one may wonder why that is. And that ultimately comes from the differences in reactors and the efficiencies of those reactors and how those compositions or the complexity of those compositions ultimately resulted from. So how was the waste generated? I want you to look at this not only from the perspective of the unit operations. My point is to show you the complexity of the waste streams that were produced and how those are the waste that are ultimately coming into the integrated flow sheet. But in general, to support the part of the U.S. defense program, Hanford had 9 operating reactors. They had 4 fuel reprocessing flow sheets, and in total they processed about 100,000 metric tons of fuel. The general kind of generation of waste flow sheet, if you will, the 300 area at Hanford was really the fuel fabrication site where they produced these unrated fuel rods or green fuel rods. Those unrated fuel rods ultimately went into one of the 9 reactors. The B reactor coming online first in September of 1944, transitioning all the way up to the N reactor coming online in 1963. Those unrated fuel or green fuel rods will ultimately produce spent fuel, if you will. The spent fuel went into one of 4 fuel reprocessing flow sheets, the first being the T plant, which came online shortly after the B reactor in 1944. What I'd like to point out is the bismuth phosphate flow sheet for T plant as well as B plant. That was a flow sheet that was not utilized at Savannah River, which will ultimately come into the compositional complexity and the differences between those compositions between the 2 sites. As the technologies matured, they were ultimately transitioned over into a solvent extraction process at Hanford, both for redox and purex. Savannah River site was mainly a purex process. They had a high heat HM modified process which produced a high aluminum feed, but Savannah River typically has high aluminum, high iron feeds. Hanford has had a multiple, if you will, reprocessing steps, which contributed to the complexity of the waste that we're dealing with at Hanford. A lot of errors going on, but ultimately the materials for the defense programs were sent to different sites. And at Hanford, this is where the waste is sitting in the 177 tanks, the 55 million gallons of waste that's currently sitting there waiting for disposal or treatment, immobilization, and disposal. So obviously the periodic table, the green boxes are the waste components that you would find not only at Hanford, but at Savannah River. The one thing that I do want to mention is that obviously that it's basically a periodic table, that complex concoction, if you will, of waste that are within the tanks. Again, those waste streams not only vary perhaps within a tank, but between tanks and between tank farms. But one thing that's not shown in this particular slide is a third dimension in terms of volume or concentration of these components between Savannah River and Hanford. I mentioned the T plant coming online with the bismuth phosphate flow sheet. Both of these are green for both sites. The bismuth and phosphate at Hanford are significant issues. On the high level waste side, they are not significant issues at Savannah River because they didn't really run a bismuth phosphate flow sheet, primary redox and HM. Excuse me, the aluminum concentrations are also pretty significantly different. When I was at DWPF, and things may have changed in the last 5 years, when I was at the lab, I saw feed vector concentrations from the system planning group that the highest feed vectors I saw then roughly around 30 to 38% aluminum oxide coming into the VIP facility or into the planning process. At Hanford, I've seen big feed vectors of aluminum oxide coming in at greater than 90 or 95%. Chrome is a significant issue at Hanford. It is an issue at Savannah River. The chrome concentrations are significantly higher at Hanford. But again, Savannah River also had to deal with a little bit of the chrome issues. I'm not going to go through all the elements, obviously, but just recognize that the differences in the reprocessing steps used between the two sites ultimately generated not only differences in the elemental compositions of the waste, but the concentrations of those waste. And you can, if I generalize this, I can think of the Savannah River sites are a compositional subset of the Hanford waste streams from that perspective. So looking at the breakdown of the waste at Hanford, again, these multiple reprocessing operations are driving some distinct compositions that we were having to deal with at Hanford. The waste is primarily the sodium nitrate, sodium nitrite mixture, if you will, and that's due to all the additives that were being used during the reprocessing process. This is primarily all the supernatant fraction, if you will, the liquid and the salt cake. That is destined, if you will, to go to the LAW side in the flow sheet, which would be critical after a while. We also have sulfate from some additions that were used in the reprocessing flow sheet. But out of the 16% others, you can see this phosphate being about a quarter of that 16%. That's that bismuth phosphate flow sheet in T and B plant, or T plant. We've got the bismuth component there. Aluminum is about half of that 16%. And you also have, which comes from the aluminum cladded fuel rods, mostly, primarily, but some aluminum was added some other places. We have zircon and silica as well. And the reason I want to point this out, these are the components that ultimately are going to drive what decisions are being made in terms of a blending strategy, retrieval strategy in the tank farms, some kind of pretreatment strategy in the pretreatment facility, and ultimately, if those components are removed up front in the VIP facility, you're going to have to deal with these specific components because they're going to drive glass formulation efforts. This slide is going to kind of show you two critical differences between the Hanford and DWPF flow sheet. And I'm going to point to this. This is a really small plot, and I apologize for that. This is a look at the feed vectors coming into the LAW VIP facility. This may be about 5 years old, so but maybe a little bit off, out of date, but the concept is still clear. This red line, excuse me, is the sodium concentration. The green line is the sulfur concentration, and this purple line is the aluminum concentration. These are feed vectors coming into the facility as a function of time, if you will, on this x-axis. So you can tell that these feed vectors are just jumping up and down pretty regularly, if not on a weekly or a monthly basis. Now that drives a huge difference in between the two flow sheets. Again, the Hanford flow sheet, the baseline Hanford flow sheet, we had the waste coming in, pretreatment was going to separate that into a low activity and high activity streams. We would add gas forming chemicals to the incoming feed based on that feed vector composition, put that into a melter, produce the glass, and then ultimately goes to a disposal. But what I want to point out is this feed vector is this line coming out of Tister into the vit facility, into this receipt vessel. And the frequency and the magnitude of these changes in these components drives Hanford to use glass-forming chemicals, individual components, if you will, to be able to have the ability or the agility and the mobility to adjust to this incoming or rapidly changing feed vector to target a glass composition to meet the melter processing constraints as well as product performance constraints of the glass. That's a huge significant difference between the different flow sheets, because if I take that and compare the Savannah River flow sheet, obviously they have waste out in their tank farms. The high level waste comes down here through there. It comes into a receipt vessel. The supernatant and the dissolved salt cake comes into the SWPF facility, where it's basically the cesium, strontium, and actinides are removed. The LAW fraction comes in. A huge difference. One of the two differences is the huge difference is that at Savannah River, the LAW is grouted and goes to a low activity disposal facility, whereas the HLW fraction, the cesium, and these sludge fraction or HLW, it is blended with a prefabricated glass. These are not GFCs. This is a prefabricated glass product designed to tolerate the incoming feed vector, because that feed vector is relatively constant over a year, if not more. It could be up to 2 or 3 years. So there's no reason to have the ability or the agility or flexibility to change the glass forming chemical concentration, because you have a constant incoming feed vector relative to the Hanford flow sheet. So let's take a little bit deeper dive into the glass unit operation. Hopefully you're getting a handle on the specific all the different unit operations of the integrated flow sheet, but this is going to start drilling down into the vit facility. Key terms: waste loading. That is nothing more than the amount of waste, which is calcined at that time, contained in each canister. So if I said I had 100 kgs of glass and it was a 20% waste loading, you would have 20 kgs of waste, and the rest of that product is going to be our 100 kgs, 20 kgs of glass or waste. The other 80 kgs is going to be the glass forming chemicals that you've added. So obviously you want to target a higher waste loading per canister, because for a given amount of waste, you're going to produce fewer canisters that you're ultimately going to have to dispose. Melting rate, you hear a lot of people talk about melting rate, and that is nothing more than the conversion of that incoming liquid feed stream to a molten glass state. This liquid feed stream is the supernatant fraction coming in with the glass forming chemicals added. That is a liquid that is fed into that melter, and that melter has to basically convert that liquid feed into a molten glass to pour glass in the cans. So you hear people trying to drive toward higher melt rates. So I'm filling canisters faster so I can produce more canisters per unit time. Those are typically the two main concepts that people think about in the vit facility. Another concept that really should be driving, or two other concepts, is waste throughput. And in terms of, this should be thought about in terms of the amount of waste you're processing per unit time. You may not be processing a maximum amount of waste at a maximum waste load. In fact, what we found when I was at DWPF or Savannah River is we found that there was an intermediate step for a non-stirred melter, that it was an optimization point in a waste loading space, coupled with your melting rate, that ultimately dictated or determined maximum waste throughput. So we weren't processing a maximum waste loading, we're processing at some intermediate waste loading, but the amount of waste being processed per unit time was maximized. That is the key factor in determining the overall mission life of WTP, as well as any other flow sheet. because you're pulling waste out of tanks faster, you're processing through pretreatment, you're melting faster, and you're processing more waste per unit time, and you're basically emptying the tank farms quicker. So that is a key concept that people need to think through in terms of that. Now that has to be integrated not only within the VIT facility, but you have to have retrievals, pretreatment, the VIT, all in kind of coordination, if you will, to make that happen. The other thing that people rarely talk about is operational flexibility. Now this is a key driver from an operational standpoint. If you're in the VIT facility operating, the engineers in the facility operating, you want large compositional spaces to operate in. You want the compositional space over which glass can be made, an acceptable glass can be made, to be as large as possible, because it gives you options in your operations that you normally wouldn't have if you have a very small operating window. So again, hopefully that concept will come up or be solidified at the end of the presentation, but is a key concept that you really need to focus on in terms of specifically the integrated flow sheet at Hanford, but maybe in your flow sheets as well, just a different application. So here's a slightly different look of the WTP or DF law, the direct feed low activity waste flow sheet. 2 different tank farms, again, where the 55 million gallons of waste is located. This flow sheet is using that supernatant or the dissolved salt cake that is retrieved. It comes into the Tiscombe unit where you do ion exchange and filtration and ion exchange. You remove the cesium, excuse me, that decontaminated salt solution comes into the VIT facility. You've got some secondary waste coming off the melter that is recycled back into the facility that you have to handle. The secondary waste are handled into another facility called LURF-ETF. And then their secondary waste are immobilized. They go to an integrated disposal facility on site. The low activity glass then comes down this particular route and ultimately goes into the IDF as well once it's poured into canisters. So again, we're focusing on this VIT facility, this green section. We talked about waste loading, melting rate, and we didn't talk a lot about operational efficiency, but this is basically the percentage of time that the facility is online. That's primarily not in the vitrification by glass formulation guys' hands. We typically focus on waste loading, melting rate, and when you bring in the operational efficiency, that ultimately determines the waste throughput. Again, we did talk about operational flexibility, but I've talked about it in the context of just the VIT facility. That operational flexibility needs to be looked at holistically in terms of that whole integrated flow sheet. Operational flexibility in the tank farms, giving people options. Operational flexibility in Tiscombe, the pretreatment facilities. Operational flexibility in the VIT facility. Those communications have to be really sound in order to maximize the overall efficiency of the whole integrated flow sheet. And that operational flexibility can actually come down and do your risk reductions, whether those are operational, compositional, or programmatic risk reduction. So here's an example of an integrated flow sheet. A lot of people might be wondering to themselves, what is pretreatment? Why would you even perform treatment? And the question I would ask is, could pretreatments actually have a negative impact? I'm going to switch gears just a little bit. This is now the high level waste side. This is the sludge fraction that we talked about. This is a study by Dong Sang Kim and John Vienna at P&L back in 2011. I understand it's 10 years old, but the concepts are still very valid. What they did at that time is they took the incoming feed vectors for the HLW facility. They calculated the maximum waste loadings for each one of those feed vectors in terms of the glass formulation, the maximum waste loading for that particular feed vector that they could achieve. But they were most interested in not only the maximum waste loading, but what dictated them from going higher in waste loading space. And for example, what they found was that almost 50% of those feed vectors were limited in waste loading space by high alumina. Remember I talked about some of these feed vectors having 90–95% alumina. Well, here's where they start showing their ugly head, because that alumina is driving the waste loading dictations, or dictating waste loading for about half of those feed vectors in HLW space. They found that chrome limited and sulfur limited about 20% of those feed vectors. They found about 10% were phosphate, bismuth phosphate flow sheet. That's where this phosphate difference is coming in. You will note that only 1% of the sodium dictated the maximum waste loading, and that's because all the sodium doesn't come to HLW, is pushed in the LAW direction. So that becomes a key difference between the two flow sheets at Hanford, between LAW and HLW. So when people, start looking at this, you go, well, if 50% of the feed vectors coming into the facility or into the vit facility are limited by alumina, another 20% is limited by chrome, what can we do? We're making a lot of canisters. We want to reduce the number of canisters we make so we can go to higher waste loadings, if you will, because we want to drop these percentages. So every component, but specifically Trouble's components, had limited solubilities in borosilicate glasses. And again, those ultimately dictate waste loadings and ultimately are going to increase canister counts. So the pretreatment facility guys started looking at that and said, hey, well, we can go after aluminum and chrome through two different dissolution steps. We can add a caustic dissolution using sodium hydroxide to go after alumina. We can dissolve the alumina, strip it out, send the alumina over to LAW, but reduce the impact on HLW space. We can do an oxidative leaching process to remove chrome. Again, strip it out of the HLW feeds, send it over to LAW, and then you'd have a higher waste loading potential in HLW space. Very effective in terms of being able to remove alumina and chrome, depending upon the form of alumina, obviously, whether it's ilmenite or gibbsite. But ultimately, it drives, you do get a significant reduction in mass for HLW, those feed vectors coming into the HLW facility, and you ultimately would produce higher or reduced number of canisters, and those canisters would have higher waste loadings for these particular types of streams that are limited. So one could easily say we're done, walk home, but you can also look at what can the glass guys do. And this was a program driven out of ORP in terms of the enhanced waste glasses, where they said, well, these calculations that John and Dawn Kim provided were based on an maximum aluminum concentration of 16 weight percent of glass and a maximum chrome concentration of 0.5 weight percent of glass. So they went off and did some significant studies looking at what could they do to increase the aluminum solubility limits and chrome solubility limits in these HLW glasses. And they've basically achieved over 25% weight percent, or I think they're up to around 30 now, and just slightly over 1.5 weight percent chrome. So what does that allow you to do? So now you have two different places that you can address this issue. This is the integration part. With these higher solubility limits, you could actually make some decisions on some feed vectors not to add caustic or do oxidative leaching, right? So now you've eliminated or minimized the need for pretreatment just by the ability to handle that in glass space. You've expanded that compositional region over which aluminum and chrome can be processed and still produce acceptable glasses. And then in addition, you've reduced the need for pretreatment. Why is that important? Not only for the number of cans that you produce, but ultimately the sodium permanganate you're adding for oxidative leaching and the sodium hydroxide you're adding for dissolution, not only to remove that aluminum and chrome, that sodium is going to go to the LAW flow sheet, not only with the aluminum and chrome that you stripped out, and you're going to add volume, if you will, to the LAW side. So if you can reduce the amount of pretreatment you need to do, you reduce the amount of sodium you're adding to the overall flow sheet, and you can have a positive impact not only in the HLW side, but the LAW side. So here was another example of when I was at Savannah River National Lab. We were looking at a specific sludge batch coming into the system from the planning group. It was a high aluminum feed. They wanted to do the aluminum dissolution, add caustic to the feed or prep tank to reduce the aluminum content in terms of that sludge mass reduction. During the planning phase, the system planning guys were looking at how effective, based on some results that Savannah River National Lab was presenting in terms of how much aluminum could be poured out. They were doing some projections on how much aluminum can be removed, and based on the sludge coming in and the form of the aluminum, you basically remove almost all of it because it was gibbsite. So they basically, the planning group said, okay, we're going to remove some percentage, a high percentage. They did a very good job in terms of projecting those low concentrations of aluminum. But what they failed to realize was that we had a lower aluminum concentration in glass for durability. So based on the incoming, the projections that we saw, we said, hey, you can't remove all the aluminum, because what we'll have to do is add that aluminum back to the frit to be able to meet the lower aluminum content for glass for durability specifications. So again, it shows you the interplay between, this is systems planning now, and it would ultimately have rolled into pretreatment, or it comes out pretreatment or aluminum dissolution, and the glass team. So again, these lines of communication need to be open, or you can find yourself in a very bad spot in the vitrification facility. You'll find in that case, you would have found yourself adding aluminum to a frit that maybe the manufacturer couldn't have made at the frit composition from, because of some limited technologies that they had. So let's now kind of shift and talk about some challenges within the vitrification process. So we've talked a little bit about this. I'm going to refer to this as a conceptual flow sheet, but ultimately this process is nothing more than converting this waste into a glass product at a 65,000 foot level. The next step down is you're basically taking the sludge or the supernatant, you're adding glass forming chemicals, you're adding a little bit of heat to produce the glass, you're pouring that glass into canisters, and ultimately those canisters of glass are going to go to a repository or near surface disposal facility. If we strip another layer off of that kind of concept, you're going to be retrieving specific sludges, you're going to be retrieving supernatants. Again, there's a blending strategy that could be relied upon. You're going to do some kind of pretreatment of that sludge or supernatant, whether it's dissolution, ion exchange, filtration, or washing. That high-level waste sludge fraction, the solids or the decontaminated supernatant, are going to be transferred in that vitrification facility. Again, based on the incoming feed vector, the composition of that feed vector, you're going to add glass forming chemicals. We're driving toward how we're controlling this process. We're going to talk about the process control strategies in a minute, but hopefully you're starting to think some kind of questions like, how do I know what glass forming chemicals to add? And how much do I add? Those are all going to be driven by this process control strategy. Once I've added my GFCs to this incoming feed vector, I've produced a melter feed. That's introduced into that melter sitting at 1150 degrees centigrade. A lot of people consider this melter the black box. That is, goes in, it comes out, I really don't care. There are a lot of complex reactions going on in what we call a cold cap that we'll discuss in a minute. You've got rheology issues of the feeds you have to worry about in terms of spreadability. You've part redox adjustments in terms of foam potential and off gas and volatility issues you have to deal with. That is a critical part in that melt rate part of that equation that dictates overall waste throughput. And ultimately that melter feed is converted into a glass product and ultimately goes into a repository or near surface disposal. Simple concept, extremely complex to implement. Implement may be the wrong word. It may be to choreograph. There's a lot of critical decisions that need to be made. Those decisions need to be underpinned technically because this is a feed forward flow sheet. That is, once that glass is made, there's no rework of the glass. That glass has to meet the durability specification as defined by the end disposal system, as we'll talk about in a few minutes. Another part of this is scaling. A lot of researchers, maybe you're listening to this talk and you're doing in the lab, doing a lot of vitrification melts. These are crucible scale melts in a lab. You may be trying to make a glass that we'll talk about in a second to measure some property. You may be looking at little small melters to look at the melt rate or volatility or cold cap behavior. But ultimately, this eye toward implementation concept I talked about earlier, you better be thinking that this is a DWPFs in their shielded cells of some process vessels within the DWPF. You've got to be able to translate all this work that you're doing in the lab scale to an operating facility, because you're not going to be making glasses or vitrifying 55 million gallons of glass in a crucible. Well, you could, it'd take forever, but you're going to be having to scale these issues to make sure that operation is efficient and effective at a very large scale. So how does that development stage what does it look like or mature? Obviously, you've got waste characterization. You know, you'd like to know the waste compositions of incoming feed vectors. Maybe that's globally, or maybe there's a tank farm you're interested in, or maybe there's a specific tank you're interested in, how we're going to handle it. Obviously, you need to know what that feed vector looks like. You can then go off and do what I call proof of principle surrogate testing in the lab. You can go make glasses in the lab, you know, use oxides and carbonates to make glasses because you really don't care how you get to the glass composition. You just need to get to that glass composition. But typically what you're trying to do is cover some space. Like I said, you're trying to cover spaces you're interested in that the facility may ultimately be processing over. You may come in and do actual proof of principle tests with actual waste. That is, you're using surrogates here. You may need to make sure those surrogates you're using are giving you the same properties or values of those properties that you're interested in. Again, you may be doing surrogate melter testing. You may actually do some small scale radioactive melter testing to look at melt rate issues, foam potential, things like that. But all these things that you're doing in the lab, again, have to be fed into these models that we're going to develop, or observations we're going to note, if you will, that ultimately lead to a process control strategy that runs that facility, makes those decisions on what GFCs to add. Can we process this through the melter? Will it meet the durability specifications where the glass is going to go to? And that's what I'd like to kind of transition into now. We'll talk about some of these process and product performance requirements, how this process is controlled, and the impact of those process control models on this acceptable composition regions, or the operating window, if you will, in a glass space or the vitrification facility. So again, I'm not going to go through this in detail again, but I will say that I'm driving, one too many, I'm driving now into this space. Remember, we had this variation in these feed vectors coming into the facility that, you know, based on the components, would go up and down on a daily or weekly basis. We have the flexibility with GFCs to react to that variation, but how do we make those decisions? You know, what GFCs do we add? I think there's 11 or 13 GFC chemicals for LAW and HLW space that we can add based on that incoming feed vector. How do you select which chemicals and how much to add? How do you know what waste loading to target to make sure that it would make it through the melter and make a durable product? We need to have compositional property models, glass composition property models, that is, models that relate the properties of the glass to the composition of the glass to be able to make these kind of decisions. And we'll talk about that. Again, we need to make sure that if one goes in that melter, it's actually going to melt at 1150, that it will meet liquid temperature, viscosity, and we'll talk about some of those in a second, as well as durability specifications, whether it's going to IDF or to an HLW space, the geologic repository. The process control models are key because once that glass is poured into a can, the glass is not reworked or is not reworkable. You can't remediate it at that point. You can potentially remediate it here if you take a composition of the melter and find that your models predict it's going to be bad. You can make some adjustments. But you really want to make sure that this feed forward process control strategy is technically underpinned or sound, because those decisions are critical with respect to melter operations and product durability. So I refer to this slide obviously as what goes in must come out, must be durable. That is, that melter feed that you come in has to go in the melter, it has to come out of that melter, and it has to be durable. So this top right diagram or schematic is a cross-section of a general melter, if you will, the joule heated melter. This slurry feed is the waste GFC mix. This is the melter feed I was talking about. It is a liquid feed. It comes into the melter through a feed tube. There's a melt pool sitting down here that's nominally at 1150 degrees centigrade. This slurry feed comes in, and hopefully it spreads across this, this glass surface and forms what we call a cold cap. The cold cap is a blanket, if you will, of transitioning from unreacted feed at the top to almost glass at the bottom. That's a pretty simplistic view, but it is a blanket of unreacted feed in which a lot of complex reactions go on. And those complex reactions for example, can induce some really problematic things, components or events in the melting process. If that initial liquid phase that forms as these raw materials start to melt is a high viscosity liquid, you have a lot of nitrates, carbonates, nitrites, all trying to come out of this system at the same time. You can actually capture those gases in a high viscosity liquid and create a foam layer at this interface. And I'll show you this kind of an example down here. This would be the incoming feed at the top that we dried. All the water's being driven off. This will be a glass pool at the bottom. And at that interface, you see all these air pockets. Well, if those air pockets are numerous and pervasive, if you will, you can actually form basically a double pane window effect, an insulating layer between the only heat source in the WTP melters, if you will, the glass pool at 1150, and that incoming feed. And if I can't transfer heat from the glass to the incoming cold cap or the incoming melter feed, what happens? My melt rate slows. I have to stop feeding. I have to let this cold cap burn off to be able to convert that into a glass product so I can actually pour glass into a can. So again, knowing all these complex reactions in this cold cap, being able to potentially manipulate or control those to avoid certain deleterious effects or reactions can actually help in that melt rate equation that we talked about in terms of maximizing waste throughput. So we talked a little bit about balancing key properties. You heard me say what goes in, what comes out. What that really means is we have processing constraints from a melter perspective. We have viscosity constraints, we have liquidus temperature, and we have electrical conductivity constraints. I forgot to mention on this last slide, this is a joule heated melter where current is being passed between the two electrodes. If you can't pass current, your melter will freeze, if you will. Your glass temperature goes down and your glass solidifies, if you will. But this is not an inclusive list. This is just three of the critical components that we have to control or make sure that melter feed, once it's in that melter, will meet these specific processing constraints. We also have product performance constraints, just generally called durability. For HLW space, it's the product consistency test A. I'm not going to get into that, but for LAW at Hanford, it's both the product consistency test A as well as the Pct response. But just recognize that you have melter constraints, or process constraints, as well as durability or product performance constraints. And it's these process control models that have to look at every one of these constraints, be able to predict them in real time, and compare them to some acceptability limits we'll talk in a minute to make sure that that melter feed that you're designing will actually make it to the melter, through the melter, and meet the durability specs. And then on top of that, a lot of the contract obligations in terms of, hey, minimum waste loadings or production rates, you have to kind of fold that into your decision-making process with these process control models. But again, these process control models are nothing more than mathematical models that relate composition of glass to the property, to a specific property. And to do that, you need data, obviously. Typically, what you try to do is you design a test matrix of glasses, a statistically designed matrix to cover some compositional space. Again, it may be a tank, it may be a tank farm, it may be a certain period of time that the feed vectors are going to be covering, but you want to cover some kind of space that you think you want to process in the VIP facility, a glass space. So you defined, a handful, maybe 20, 30 glasses within a study. You've statistically spread those out in that multidimensional composition space, and you go make these glasses in the laboratory using oxides and carbonates. You melt those glasses and you pour a glass product like we're showing over here on the left, and we'll see a video in a second that we're targeting this specific glass. Then you go measure the properties, and now you have a relationship that you can develop over that space that you cover between the property of the glass and its composition. And those are what's used to develop the models that support facility operations. Let's see if this will work. So this is going to be very jumpy. Bandwidth is killing me, but this is a technician in the lab. Basically, somebody's handed her a batch sheet to target a specific composition for one of those 20 or 30 glasses I'll talk to you about in this test matrix. There may be 20 or 30 different components of this glass that she needs to target. She'll weigh those out, and she'll notice she's using reagent grade compositions or reagent grade chemicals. And she will ultimately batch all that up and put that into a platinum crucible. Let's see if this video will play. So, looks like I'm locked. Here we go. It'll probably skip because I've touched this thing. So here's those raw materials have been put into a platinum crucible. This particular technician is going to pour this into a stainless steel plate. What will result is a glass pour patty, if you will, that now can be used as a sampling stock to measure these properties of interest, whether it's viscosity, electrical conductivity, durability. You know the composition of the glass you made, you can measure the properties, and that's how you're going to get these composition property relationships. Let's see, did I skip one? Nope. Sorry about that. So what properties will you be interested in? We talked a little bit about them a few minutes ago. Crystallization is obviously a significant concern in the melter. This is associated with the liquidus temperature, which is a temperature which, if the liquidus temperature of the glass is above the nominal melter temperature, you have crystals that can actually form in the molten glass pool itself, or actually within the cold cap, and either grow or settle within the glass system. Here's a laboratory crucible where this is the bottom of the crucible. These are spinels that are formed in the bulk glass, and they're basically just raining down and precipitating and basically forming a layer at the bottom of the crucible. If that happened in a joule heated melter, you had a spinel layer at the bottom. Those spinels are conductive, so the joule heat would actually, the current would actually start coming through the spinels and not through the glass, and that would have a detrimental impact, obviously, through the temperature of this glass, and you ultimately could wind up having to change out a melter. So obviously you need a model to control or limit the ability of crystals to form in this melt pool because of the negative impacts they can have, not only in the shorting out a melter, they can also clog pore drains, pore spouts. These temperatures tend to drop a little bit in relative to the nominal 1150, and they may actually disrupt flow within the melter in terms of a homogeneous type system. So viscosity is another critical melter processing constraint or property we're interested in. Again, we need a model to predict viscosity as a function of temperature and composition. The reason we need a viscosity control is if the viscosity is too low. I failed to mention that these melters are generally lined with some kind of refractory, like a K3 refractory. The melter viscosity being low can actually increase refractory wear. It can also increase corrosion erosion on any kind of materials that you've introduced. This may be a bubbler designed by, say, DSL to improve melt rate. You can actually potentially reduce the life cycle of not only the bubblers, but the electrodes. And in general, you actually increase volatility of certain components if the viscosity is too low. If the viscosity is too high, then you have basically you can have incomplete melt homogenization that can be kind of overcome with bubblers. You could have hindered or inability to actually pour glass. If the viscosity is too high, maybe not make out of the throat. And if the viscosity is too high as it comes out of the throat, you may not fill the canister because of viscosity. What you would like to see is the glass being poured into the canister spread across the cross section of the bottom of that canister as it's being filled. But if the glass is too thick, it may stop and not fill, and you may have a partially filled canister. So again, the ability to control viscosity and understand viscosity before you introduce that melter feed to the melter is critical. Another significant impact is sulfur. We talked about that in one of the pie charts back. That's a component that was added in the reprocessing steps. This is if the sulfur solubility limit is exceeded. This is a picture taken by Keith Matlick of VSL, where they took a threaded aluminum or metal rod into the cold cap, and they basically, this was a melter test to look at sulfur solubility, and obviously they've exceeded it here unintentionally. And you can see this yellow salt that's sitting on the surface. This is a very aggressive salt layer. It will impact K3 refractories. It will bore holes through them. It will increase the volatility of cesium and technetium out of a LAW system. So again, avoiding salt formation is critical, and having a model that predicts, sulfur solubility or something like that is critical in those process control strategies. Chemical durability is another component that's on the product performance side. Obviously, the main objective of the whole flow sheet is to immobilize these hazardous and radioactive components in the glass to meet some kind of long-term performance metric. I mentioned the PCT, product consistency test A, is the durability requirement for HLW at Hanford, as well as Savannah River. For LAW glass in Hanford, you have both the PCTA as well as vapor phase hydration test. Again, 2 tests that you can run to be over a compositional space to develop models to be able to predict the durability response as a function of composition for unknown glasses within that space. So this is a slide that I hesitated a little bit on putting in here, but I have the word general underlined. These are general composition property relationships, and I want to be very clear they're general. This is over a specific compositional space. It may not be applicable to a larger space or a different space. I want to make that very clear. If you look at the oxides and the properties, I'll just pick a couple. If you increase the aluminum content within this specific space that we looked at, that John Bien and Dawson Kim looked at, viscosity generally increased. The electroconductivity basically had very little of minimal impact. PCT, this is a little bit tricky. This is the PCT response. The PCT response, the actual durability increased. This is the response, it decreased, but the durability increased. But after some point, the aluminum concentrations actually made the PCT worse. And that's shown over here, that when you take a specific glass and you actually start increasing the aluminum concentration, the PCT response in grams per meter squared will actually start to go down. That means the PCT is getting better, the durability is getting better, but at some point, that inflection occurs and the durability will go up. So you have non-linear things that are occurring. Obviously, I'm not going to go through everything, but you've got errors going in every different direction. So you can't make these decisions on the fly by yourself because you've got a multi-component compositional feed vector coming at you. You've got GFCs you need to add, and you need to predict these responses as a function of all these components for that glass that you're targeting. Extremely complex system. That's the reason you're relying on these process and product control models to guide you to make low risk decisions, no risk decisions, if you will, probably low risk decisions for the GFCs you're adding to that incoming feed vector to make sure that the feed vector you're sending into that melter will make it through the melter and the product that you produce will be a durable product and meet the specs. So here's a short list of the LAW property specs. The LAW glass coming out of the LAW melters in Hanford have to meet the PCT test, the PCTA, and the bar that it has to meet is less than 2 grams per meter squared. I don't have a lot of time to go through that, but there's a metric there that if the glass, when you run this specific test, if the boron, sodium, or silica release is greater than 2 grams per meter squared, it is an unacceptable glass composition. It should not be processed through the facility. So again, you need a model that's going to predict that PCT response, and you need to compare that prediction to this particular constraint to decide whether it's good or bad glass. And that concept's important. You've got viscosity constraints, high and low viscosity. We talked about that earlier. You've got electrical conductivity constraints. You've got waste loading constraints. You've got all these constraints, and you've got some kind of acceptability criteria that has to be met in order for it to be an acceptable glass. All that is kind of bundled up into a document that John Bien and Dawson Kim wrote for LAW for the baseline glass compositions. Ultimately, these models roll up into an algorithm that basically prescribes the appropriate mix of LAW and GFCs to add to each batch to maximize operational efficiency, if you would. And again, they're nothing more than these glass property and compositional constraints that are being looked at in terms of acceptability. So all that to get to this one plot. So this is a plot that hopefully will try to bring everything together. This is a two-dimensional plot trying to represent a multi-dimensional compositional space. You can consider this to be either high-level waste or low-activity waste, take your pick. We'll take this end member down here to be a specific GFC or a combination of GFCs, and we'll take this end member to be the other fraction of the GFCs that you want to add. Feed vector coming in, GFCs to add. Now I can take those two and look at waste loadings from 0 to 100%, and I have a huge space in composition space. It's basically a multifaceted hypercube, if you will, that shows me all the different areas, the range of alumina concentrations I could process, the range of chrome, whatever. So now I've got property models and I'm going to overlay. We've got constraints for liquids. We have constraints for viscosity or conductivity. We have constraints for durability. We have minimum waste loading constraints. So if I look at viscosity, we have an upper and lower viscosity. When I look at that entire multidimensional space, this side of this triangle, if you will, out here, basically says those glasses don't meet my viscosity constraint. You should not process those. The liquidus model will start to partition, it'll cut off this space. You should not process because you will form crystals in the melter that may either clog a pore spout or result in a melter failure. Durability, it will cut off this space. And this is obviously generic. You may have some minimum waste loading requirement. It says you can't process at these low waste loadings. We want you to force you to go toward higher waste loadings toward this particular corner of the ternary, if you will. So what these models do is they ultimately define what I'm going to refer to as an acceptable compositional space. This box that's outlined in this little triangle. But these models and these measurements also have uncertainty. So once you apply the uncertainty of these models, compositional measurement, all the uncertainties that the statisticians love, that box ultimately shrinks more. And this is the operating window that I talked about earlier. This operating window, ultimately what you're going to do is you're going to target some composition. You're going to have to account for a lot of different uncertainties, but you want those models to guide you into what space that you should be in with the highest waste load you can target and still meet all these other these processing constraints or product performance constraints. That is what the models are going to drive you toward. Now, in terms of operational flexibility and the R&D that you're doing in the lab in terms of risk reduction or uncertainty reduction, what should you be aiming for? What you should be doing is you've got a baseline liquidus model, you've got a baseline viscosity model, you've got baseline durability models. You should be looking to those models to reduce uncertainty. And if you can reduce those models either through measurement uncertainty or develop a new model, you can push the boundaries in the opposite direction, and you can actually start to increase. You can push them in all directions. This line would go this way, this line may not move because of minimal waste loading, but this line may go up. And there's multiple constraints here. But you can reduce that uncertainty. You can start to open up that compositional space. And what does that compositional space allow you to do? Think back to the aluminum chrome issues. The higher the aluminum content in glass, the less I may have to go make decisions to do aluminum dissolution or oxidative leaching. I reduce the amount of sodium going into the system that LAW has to deal with. So facilities like to see huge operating windows. That gives them flexibility to make decisions. That gives them flexibility to change things. If they're operating on a very small window, they are very nervous, and it is a rough place to be in because of the facility operations. So hopefully that drove that home. I'm not going to go through this slide, but those are the measurement uncertainties. You can look at those. The real driver here, we've talked about these incoming feed vectors for LAW. Those models are really required in the algorithms that I pointed you to on that document. You need to make real-time decisions. You don't have time to wait. The feed vectors and the processing or the production schedules are extremely aggressive. You need to make decisions fast, and those decisions need to be low risk in terms of the melter feed processing as well as the product performance constraints. That's the key of these models. The last couple slides here, I want to talk about some impacts. This is the EWG program, the Enhanced Waste Blast program out of ORP, the DOE office at Hanford. This program is under the direction of Albert Kruger. He's looking to expand that compositional space. That is, we've got baseline models that control both HLW and LAW. But if you look forward and you want to expand or give the operational flexibility in terms of operating, or even pretreatment, or maybe the tank farm impact those decisions, that larger processing window is going to be key. So Dr. Kruger's program looks at expanding these regions, developing new models, reducing uncertainties or within those models to increase compositional space. He's looking at techniques of halide retention, crystal tolerant glasses, nepheline formation, melt rate, melt and cold cap dynamics. All these factors that fit into waste loading, melt rate equals that waste throughput, and expanding the compositional space. Here's an impact. We talked about the aluminum going from 16 to greater than 25 and the impact it has on pretreatment. We talked about the chrome going from basically around 0.3 or 0.5 up to about 1.5 and the need to reduce oxidative leaching and pretreatment. And we haven't talked about sodium. Sodium is primarily on the LAW side, as I mentioned earlier, and the baseline was at 20% sodium, maximizing 20% sodium in glass, primarily for durability or low viscosity reasons. Albert's programs have taken that to 24% on these enhanced waste glasses, and that doesn't look like a lot, that 4 or 5% increase. They may be slightly higher than 24, but that is a significant reduction in LAW glass mass that's going to get reduced. Here's some calculations that John Vienna and Don St. Kim did as well. These baseline models that were used, they were going to generate about, this is HLW, I believe, they were going to generate about 18,000 canisters. With the enhanced models going to higher waste loadings, they basically cut that in half, or over half, if you will. So again, these models, if you continue to challenge the baseline models to increase operational flexibility, they have significant impacts on life cycles of the overall facility. Again, I'm not going to go through this, but the VIP facility is driving toward these. But again, I want to reiterate that if you optimize the VIP facility, if pretreatment can't keep the facility fed, or the tank farms can't keep TSCR fed, that's a problem. The integration of these components of these different unit operations is key. We've talked about it. VIP facility can do things, open up windows that allow pretreatment and maybe the tank farm operations to make other decisions than they would be making. So I think this is one of the next to last slide. I'd like to throw out a couple operational thoughts. Hope you find this somewhat intriguing. We talked about this integrated flow sheet. We talked a lot about not focusing on optimizing a specific unit operation, whether that's tank farms specifically or pretreatment or the VIP facility, but you need to look at the systems approach. You need to look at optimizing the entire flow sheet instead of optimizing a specific unit operation. Not saying those are mutually exclusive, but generally you need to be thinking about how do you optimize total waste throughput and operational efficiency. And to do that, open lines of communications among all the unit operations are key. You need to share your knowledge of the advancements you've made, the limitations you may have, the concerns or unknowns you may have, and do not work in a vacuum. You need to, excuse me, you need to avoid implementing things that may cause downstream impacts. And I've talked to my tank farm people, I've talked to the pretreatment guys. Anything that's added to tank farms into that flow sheet, into the process, it ultimately flows downstream through this flow sheet. And if it's not taken out, the VIP facility has to deal with it. If it is taken out, it better have a disposition path. So again, things upstream have huge or can have huge impacts downstream. Be vigilant of a changing flow sheet. That is, you'll probably in your line of work, you develop a flow sheet for a specific unit or a specific task. That flow sheet is defined, but it ultimately is likely going to change. In the VIP world, it does change. You may plan on some kind of retrieval process that may not work out. What you really need to do is stay focused and out front of those changes. You're not going to be able to predict everything, but you better be trying, at least in the VIP facility, as well as these other unit operations, to increase the operational flexibility within that unit operation so you can absorb or tolerate those changes that are unknown that are coming down the pipe. And ultimately, stuff does happen. You know, you need to reduce that risk in advance. We talked about you can't predict anything, but again, the ability or the need to maintain and establish critical platforms of capabilities, regardless of the unit operation, those are critical to ensure that if an emerging issue surfaces, you have the ability to respond to that emerging issue effectively, safely, and efficiently to avoid downtime in a facility, regardless of the unit operation. So with that, so here's kind of the historical overview. Back in the 40s and 50s, a lot of plutonium productions for defense programs. Again, the waste were generated to 55 million gallons of waste in those 177 tanks at Hanford. Present day, currently safe operations, safe storage, and we are transitioning within the next year or 2 years, if you will, to start feeding the direct feed low activity flow sheet with transferring supernatant into the LAW VIP facility. With that, I apologize for running a little bit long. Any questions or comments I'd love to address. Thank you for your attention too.
Thank you, Dr. Peeler. If you have questions, go ahead and type those into the questions pane. While questions are coming in, we're going to just take a quick look at the upcoming webinar presentations.
Bert, can we advance?
Yes, please. I was going to say, I don't know why you and I are, it should give me the.
Yeah, not letting me advance.
There we go. In March, a presentation on introducing new plant design code. In April, experience of HTTR licensing for Japan's new nuclear regulation. And in May, a presentation on the advanced manufacturing for Gen 4 reactors. So there's several questions that are in the question pane. Dr. Peeler, can you see the list? The first of which that I show has, does Hanford have any separated or mostly separated actinides of any type that could be consumed in a molten chloride salt fast reactor instead of stabilizing and wasting these fuel sources by putting them in the whip?
Ed, I appreciate the question. I am not a molten salt reactor expert, so I would like to defer that, and we can potentially handle that offline. I could get you into contact with some molten salt reactor guys on site that could probably answer that question better than I. I don't want to speculate.
Okay, thank you. And the next one is the idea with VF law to retrieve supernatant and dissolve salt cake, then whatever sludge is left in the tank will be there for future retrieval?
Yeah, John, good question. Yeah, that's part of the strategy that's being considered by DOE, whether that's headquarters or ORP. Obviously, the initial flow sheet is going to be to retrieve the salt cake and supernatant for the direct feed low activity flow sheet. There are considerations, I will say, on what the sludge component may look like. And I will just say an option that is being considered is direct feed HLW. That is, you can almost think of that, if that does come to fruition, you can think about that as almost Hanford flow sheets really kind of starting to look more like the Savannah River flow sheets, where sludge goes to HLW and the supernates go over to the salt waste processing facility. Again, the difference being at Savannah River, the LAW is put in a grout for on-site disposal. Hanford, LAW be glass. So yeah, John, they're considering what's next for those HLW side, but that is a direct feed HLW flow sheet is being considered or being thought of. Hopefully that answered it, John.
Thank you. A number of years ago, probably during the early design phase, the WTP was supposed to run approximately 30 years to process the Hanford tank waste. Is that still the projected timeline?
The short answer is no, but I'm going to defer any kind of mission-like questions to DOE ORP. I don't want to speculate on a mission-like number. But Gary, I could, if you send me an email, I can probably get you in line with a specific person at ORP that can answer your question. I just don't want to speculate and have that have a erroneous number out there.
Thank you. Gary also has a question about how the aluminum oxide and chromium concentrations are determined.
Again, I'm not an analytical chemist, but they actually do pull tank samples from the different tanks, whether that's supernatant or sludge samples. Those samples are transferred over to the radioactive processing lab at P&L, where they do a myriad of analytical techniques. And again, Gary, I'm not going to speculate on what technique that they use to make those specific measurements, determine concentrations. But again, if you send me an email, I can definitely get you to a person, probably Carl Poole at RPL, that can answer those specific questions and the types of equipment that they do use to. And they are a full suite of state-of-the-art equipment they use to analyze these sludge compositions or sludges and supernatants that get into the facility. So again, I'm going to have to kind of bow out on that one.
Thank you. The next one is what kind of methods are used for the separation of cesium, strontium, and the actinides?
The TISCR system right now is a ion exchange system. They've looked at different ion exchange media. Tesco, what I'm going to do is, again, I will get you in contact with a specific or a subject matter expert on the TISCR system to what ion exchange media it is, a CST, I do believe, to remove the cesium and strontium as other actinides in that particular flow sheet. But again, if you send me an email, I will get you in contact with probably Reed Peterson for that particular question.
Thank you. There's also a question on how you treat volatilized nuclides during vitrification.
Yeah, there's in LAW space, the concern is technetium and iodine, obviously. Right now, there's actually I'll call it a feedback loop from the off-gas unit back into the VIP facility. So that is a closed loop right now. There has been, again, not saying it's the baseline, there has been considerations of if you could break that, break that loop, but right now it is a closed system. Hopefully that answers your questions on tech and iodine in LAW space. HLW space for Hanford, I don't know because that flow sheet is not really defined. And your next question says, where do you dispose of vitrified HLW? Again, that's a question above my pay grade. I'll just say a undefined geologic repository for HLW. LAW glass in Hanford is being disposed of at the Integrated Disposal Facility, which is a near surface disposal facility that's located on the Hanford site.
Thank you. Seems like a very important issue is maintaining batch homogeneity. How are batches maintained, and how is a batch defined by waste tank, by process tank, et cetera? How are those samples pulled to define these batches? And if so, how are they ensured to be representative?
Ooh, a lot of questions there. Homogeneity is extremely important. Everything from pulling a sample in from the tank and how you mix the tanks before you pull those samples, the number of samples that you would pull to get a statistical analysis, how you maintain homogeneity through the pretreatment unit operation. So again, I'm not going to speak to homogeneity within the tank farms or the pretreatment facilities. Within the vitrification facilities, the different vessels are actually stirred. There are certain sampling technologies that have been used to pull samples. Those samples are currently being taken to an analytical lab for analysis There are some efforts ongoing to look at online monitoring capabilities to do those analysis, to reduce turnaround times, as well as transfer and alar issues. But within the BIP facilities, particularly the CRV or the MFPV, those samples or those tanks or vessels are stirred before samples are taken, whether that's just the waste or the actual melter feed at the MFPV, melter feed prep vessel, sorry about that, where they've actually added the jet glass from the chemicals. Because ultimately, and it's a good question, Evan, once you've added those well, in terms of the context of this presentation, the LAW comes into a receipt vessel called the CRV, concentrate receipt vessel. A sample of that LAW is taken. That sample is analyzed, and that analysis is what is going to be fed into those process control algorithms to dictate or determine what GFCs you're going to add. So again, it's critical to have a representative, homogeneous sample of that CRV vessel, because decisions you're going to make on what GFCs to add ultimately going to be dictated by that sample. Once those GFCs are added, there's another sample that's taken in the melter feed prep vessel, which is the melter feed. That sample is also pulled. It's very critical for homogeneity because you're going to pull that sample, you're going to analyze its composition, and now you're going to run that composition through your process control models once again to predict the properties that give you the green light or red lights, if you will, of acceptability or non-acceptability for all the constraints that you're interested in. So homogeneity within the BIP facility is key in terms of sampling and the ultimate decisions you're making using those process control models. Does that, hopefully that answers that question, Seven.
Thank you. And then Ed has a qualification on his question that you had addressed earlier. Do separated or fairly separated actinides exist at Hanford before stabilization?
Separated or fairly separated exist. Well, there are cesium capsules that are at Hanford, but again, I am unaware of actinated or separated actinides. I'm not saying there aren't, Ed, but I am unaware of any other separated actinides at Hanford that need a disposition path, if you will. But again, send me an email and I can definitely get you in contact with somebody to again better address that question.
Thank you. Is there any problem or effect of platinoids such as ruthenium, rhodium, palladium on glass melter operations for high-level waste?
Those concentrations are extremely, extremely small. They do act as nucleating sites for crystals. And so you look at, there have been some studies that look at the nucleation process on crystallization relative to the crystallization issues in melter processing. But typically those are in the concentrations that Hanford and even Savannah River are dealing with, they're not a melter operation issue, a significant melter operation issue, I'll say that. Now, there are other systems I'm aware of that those at higher concentrations can cause a lot of problems in melter processing.
Thank you. Have you tried any type of plants that can absorb radionuclides from contaminated soil?
I'm sure our environmental remediation groups have looked at different bio impacts, if you will, in terms of the subsurface, in terms of absorbing radionuclides. The process I talked today are basically the tanks. I don't want to jump too far out here, but you're not going to put any kind of pretreatment step, or at this point, I don't think you put any kind of pretreatment step for the volume of sludge or LAD you're going to process in terms of adding plants to absorb that. You've got a pretreatment facility using ion exchange media to capture the cesium and radionuclides. But for soil and groundwater, I'm sure there have been many studies at Hanford by P&L that have looked at plants absorbing radionuclides that may be in the subsurface. And Ahmad, I'd be glad to get you in contact if you send me an email with a particular person, a division director in the environmental remediation technology section.
Thank you. Do you completely remove nitrates before feed reaches the melter to avoid thermal input necessary to destroy them?
No, the short answer is no.
Thank you. So are the CRV vessels isolated and define the batch, and the batch is not really continuous?
You can think of this process as a batch process. Obviously, you've got a 1,000,000-gallon tank that's being retrieved from in terms of supernatant. It will come in and feed. There are intermediate feed tanks between the tank and pretreatment. Those feed tanks will feed pretreatment. The volumes, I don't want to speculate, or I don't want to throw out numbers because they are absolutely eluding me now in terms of the volumes, the whole tanks, if you will. So this is what I would call almost a semi-continuous process. The CRVs are small vessels, relatively small vessels relative to the tank farm tanks. So yes, this is kind of a batch process, if you will. The trick there is to empty and fill and empty those tanks as fast as possible to keep the flow sheet in terms of optimization. Steve, I hope that answered your question, but it is kind of a semi-continuous batch process.
And then the next question is, if waste plus additives is glass, it sounds a lot like liquid waste plus cement equals concrete. I thought the glass was melted sand. How does waste plus additives make glass?
Good question, Michael. You can take sand and melt it at high temperatures and have a pure silica glass, right? You can take a next step. If you don't have the melting temperatures high enough, you can add boron to that and make a borosilicate glass. You can then add sodium and drop the melt temperatures. But what you have to remember is you're trying to immobilize the waste in the tanks. That waste, if you go back to the periodic table, is a concoction of just basically the periodic table you're having to deal with. So it's not as simple as just adding silica. Silica could be used to make a glass. You could add, take the waste plus, being very abstract here in general here. If you took the waste plus silica, you may need really high operating temperatures. Well, those really high operating temperatures may significantly increase volatility. So what you're trying to do is you're trying to take your glass forming chemicals and balance all those different properties, whether it's melt temperature, viscosity, durability, because you don't want to just add silica, all right? You need to add different GFCs to do different jobs, if you will, on the properties of interest. So it really is a waste plus the GFCs that you want to add equals plus heat equals glass. And you're very right. It's the same as, liquid waste plus cement equals concrete. I would ask kind of in the parallel, if your cement had 3 components, would you just make it out of, maybe you could just make it out of fly ash, but maybe you want to add something else to optimize the property of the concrete. Maybe that analogy helped you out a little bit. Hopefully it did.
Do you do cementation of waste with magnesium cement or Portland cement?
Again, this is a vitrification talk. Ahmed, I would defer to you to a guy named Matt Osmundson at P&L, who is our grout formulation expert in the facility, to talk to you about the additives that they use for the secondary waste that are being handled at Hanford. So again, just send me an email. I'll be glad to get you in contact. Which rating? Teshu, that question is a little bit outside what I would be comfortable speaking to. I'd prefer to either take that offline or send me an email and I will try to get you in contact with someone, but I'm not going to speculate on that one. I have I'm just not going to speculate.
Thank you. Thanks everyone for participating with your interaction and the Q&A. It adds so much value to the presentation of what was already a wonderful presentation. Thanks again, Dr. Pila, for sharing your expertise and taking the time to spend with us this morning. I apologize for our late start and a little bit of extra energy I added.
Again, Berta and Patricia, I greatly appreciate the opportunity to talk.
Yeah, and thank you again. Wonderful presentation. And again, we had a good set of questions. So thank you for the audience for the participation. We always like you asking questions. Thank you again.
Yes, thank you for the audience.
Thanks, everyone.
Bye-bye.
Bye-bye.